Okay, let's close this little board note video with two examples. The first is problem 6.14 in your book. We have sort of a U-shaped piece with a point load going up at the tip and down at the tip, and the question is, what's the change in the size of the gap? EI is uniform, and we want you to use Castigliano's theorem to determine the size. So, obviously hit the pause button, see if you could do this, because this is a beautiful kind of little exam question, right? I mean, there's, nothing nicer than that one. So, first of all, we recognize that we have symmetry, so we're just going to look at half the problem, this half, the top half, for instance, and then just whatever we get, we're going to multiply it by 2, and that'll be the final answer for the whole gap. And then we break up this U-shaped, horseshoe-shaped thing into two pieces, a straight piece, and m is clearly px, and partial m, partial p is clearly x. We're using Castigliano's theorem. And we've got this little curvy part here where it's r times theta. So p, the moment, is p times l plus r sine theta. So it's pl plus pr sine theta. And partial m, partial p, of course, is L plus r sine theta. So don't forget the 2 here. So delta is 2 over EI times the integral of the first part, which goes from 0 to L, plus the integral of the second part, which goes from 0 to pi over 2. And a little bit of expansion here, and I get a nice little answer. I hope that's right. I think I checked in the back of the book, and I don't think that's exactly what he got, but check my math. Okay, one more example here. Super sweet. Little lead into the next lesson, though. So suppose we're seeking a displacement of a cantilever beam, and it's subjected to uniform load delta. And we want to know what is the displacement at the tip using Castigliano's theorem. But the problem is there's no load at the tip. So the way we have to do this is add this fictitious load, P, then do the partial derivative of the m with respect to P. Do that first, and then set P equal to 0, because P doesn't exist. If it sounds complicated, it isn't. You might have to hit pause and rewind a few times. So I add this fictitious P. I have moment is P times x plus wx squared over 2, x going from the left. So partial m partial p is x. My integral is m times partial m, but now I strike the p, so I just have wx cubed over 2. So I have WL to the 4th over 8, which is, of course, the expression for the cantilever beam, so I give myself an attaboy.